In section P.3, we are going to go over radicals and rational exponents. If b squared equals a, then b equals the square root of a, where you can see in the center of your screen the square root symbol. And if I'm using a computer that doesn't let me do mathematical symbols, you may see me do SQRT with some parentheses, and that means I want you to take the square root. Let's look at a few examples. The square root means what times what gives me the number inside the symbol. So the square root of 25, what times what is 25, and you'll get 5. Next, what is negative square root 49? Since negative is on the outside, the negative is going to stay. And what times what is 49? And you would tell me 7. Now let's take a look at the next one. I have big square root symbol, 9 plus 16 inside the square root. So thinking about PEMDAS, whatever is happening inside the square root sign, I need to do that computation first. So 9 plus 16 is 25, and big square root sign around that. And then square root of 25 we know is 5. However, let's look at the difference between the next example. This one says square root of 9 plus square root of 16. This time I'm going to take the square root individually. So the square root of 9 is 3, and the square root of 16 is 4, and when I add those together I get 7. So you can see these two problems are not equal to each other. Let's take a look at two rules, the product and quotient rule for square roots. If I have a big square root of a times b, I'm allowed to separate that and call that square root of a times square root of b. Now the quotient rule, if I have big square root of a over b, I can separate that out and call that the square root of a divided by the square root of b. Let's take a look at how to simplify a square root. Now, not everything is going to be a perfect square, but we are going to simplify it if we can. I personally like to use what I call the tree method for simplifying. Although there's other techniques, I like to use this one because in a little bit what happens if we have a cube root or a fourth root. The tree method is going to work every single time, no matter what type of root you need to compute. So square root of 200, we're going to do a tree. So what times what is 200? So that's going to be 2 times 100. What times what is 100? That's 2 times 50. What times what is 50? So that's 2 and 25. And what times what is 25? That is 5 and 5. Now, once you can't go any further, the next thing would be like 5 and 1 or 2 and 1. Then you stop. You don't want to go until you hit the ones. So this is what I call the bottom of my tree. Alright, and since I'm doing a square root, I'm looking for pairs. So let me change the color for clarity. I have a pair of 5s down here. I have a pair of 2s down here. And I have 1, 2 left over. So when I compute to simplify, every time I have a pair of something, it comes out of the square root symbol. So I have a pair of 5s, a pair of 2s, and then one single 2 stays inside the square root sign, and that will simplify to 10 square roots of 2. And that is your final solution. That is equivalent to saying square root 200. Let's take a look at a couple more examples. the square root of 6x times the square root of 3x. In this particular problem, it'll be easier to multiply the numbers and put it over a big square root sign. So 6 times 3, 18, x times x, x squared, and big square root around that. So 18 is not a perfect square, but we can do a tree to simplify it. That's 2 and 9, 3 and 3. I have a pair of 3's with 1, 2 left over. Just like I can do a tree with numbers, I can do a tree with my letters. That's x times x. I have a pair of x's, so the x is going to come out. So this is going to simplify here to 3x, 2 remain inside. So 3x root 2. Final answer there. All right, let's take a look at the next one. I have square root of 48 x cubed divided by square root of 6x. Again, let's divide first. 48 divided by 6 is 8. Exponent rules from the last section don't go away, so don't forget your previous sections of material. X cubed divided by x is actually x squared. Exponent rules, right? When we divide, we subtract the exponents, so 3 minus 1 is 2. Big square root around all that. Again, 8 is not a perfect square, so let's do a tree. That's 2 and 4, 2 and 2. I have a pair of 2's with 1, 2 left over. Again, x squared is x and x, pair of x's, and so this is going to simplify to 2x root 2. Final answer. Next, let's take a look at adding and subtracting square roots. When we add and subtract, think like terms. So, for example, if I have square root of 7 plus 3 square roots of 7, all right, that first one, if there's no number in front in math, that means it's the number 1. So like terms, think of square roots like variables. That's going to give me 4 square roots of 7. Next, let's take a look at rationalizing the denominator. In math, when we have a fraction, we don't like to have square roots in the denominator. So we're going to do some manipulation to remove the square root from the denominator and put it in the numerator. All right, for this first example, if in my denominator I just have a single term, in this case square root 6, then I'm going to multiply top and bottom by that denominator. Remember in math, whatever I do to the bottom of a fraction, I have to do to the top of the fraction to make it equivalent. And then multiplying fractions, I multiply straight across. A whole number times the square root remains side by side. So 2 times square root of 6 is 2 square roots of 6, all divided by. And now square root of 6 times square root of 6. 6 times 6 is 36. Square root symbol is still there. And square root of 36 is 6. So that gives me 2 square roots of 6 over 6. And now I can simplify the numbers out front. 2 over 6 can simplify. 2 goes into 2 one time. 2 goes into 6 3 times. And if you don't want to write the 1 in front, you don't have to. That's square root of 6 over 3. Final solution. All right, let's take a look at this next example. All right, what happens though when I have more than one term in my denominator? So for this example, I have 2 over 1 plus square root 5. All right, I need to still rationalize the denominator because I don't want the square root of 5. However, I can't just multiply square root of 5 top and bottom like I did on the previous example. It just won't work. I'll still end up with the square root in the bottom. So I have to use this new technique called multiplying by the conjugate. So what is the conjugate? So if I have square root of a plus square root of b, its conjugate is square root of a minus square root of b. And vice versa. If I have square root of a minus square root of b, its conjugate is square root of a plus square root of b. In order to multiply, we have to remember a multiplication technique called FOILing. So that stands for first, outside, inside, and last. When I multiply two conjugates together and I FOIL, my outside and inside term will end up canceling out and you'll be left with just F and L. So let's take a look. Square root of a times square root of a is the square root of a squared because there's two of them. Outside, I have square root of a times negative square root of b, so that gives you negative square root of a times square root of b. Now, inside, again, I have the same thing, this time positive square root of a times square root of b, and then my L term is going to be negative square root of b squared. And so as you can see, these two middle terms are exactly the same, except one has a minus sign and one has a positive sign. So when I add them, those two guys cancel out. And now square root of a squared, the square root and the square are opposites of each other, and that cancels out, and you're left with just a minus b. All right, so let's go back to that example and compute. All right, I have 2 over 1 plus square root of 5. I'm going to multiply by the conjugate, which is 1 minus square root of 5. I'm going to put in some parentheses and multiply. On top, it's just distributing. 2 times 1 is 2. Again, whole number and square root side by side, 2 square roots of 5. On the bottom, I'm going to go ahead and show out all my steps. As you get the hang of this, you might start skipping the O and the I, and that is okay. Although I do like you to show some work, so it won't hurt to FOIL completely. So let's do it. 1 times 1 for F, that's 1. Outside is 1 times negative root 5, so minus 1 root 5. Inside, positive 1 root 5. And last is minus root 5 squared from the formula above. And so, let's see. I have negative 1 root 5, positive 1 root 5. That's that O and I said that was going to cancel out. Let's copy down. Numerator stays the same. Denominator, I'm left with 1 minus square root of 5 squared, or square root of 5 times square root of 5 is square root of 25. Square root of 25, I'm back at 5. And then this is going to be 2 minus 2 root 5 over negative 4. And then it so happens that this problem simplifies. I got 2, 2, and 4, so everything reduces by, divides by 2, right? So this is 1 minus 1 root 5 over negative 2. And we'll just leave it like that. The next thing I want to mention is nth root. So if the nth root of a equals b, that means b to the n equals a. So let's take a look at the cube root. The cube root this time means what times what times what gives me that value. So cube root of 8 specifically, so what times what gives me 8, and you would tell me that's 2. Alright, let's look at the tree method with the cube root. So before, when we did square root, we were looking for pairs to take out of the square root symbol. This time with the cube root, we're going to look for triplets or triples to take out of the radical symbol. So let's look at 24, same tree as we did before. So that's 2 and 12, 2 and 6, 2 and 3. This time, let me change up the color. I'm going to change to blue so I can see my triplet. I have a triplet of 2's with a 3 left over. So this means I take out 1 for every triplet, so I have a 2 that comes out, cube root, a 3 left over. So that's the simplification. Cube root of 24 is equivalent to saying 2 cube roots of 3. Let's take a look at this definition of a raised to the m over n. So what happens if our exponent is now a fraction? So a raised to the m over n is now going to be the nth root of a to the m. And I can rewrite that in 2 different ways. Those 2 statements I underlined in blue are equivalent. So let's take a look at an example. If I have 27 raised to the 2/3, I'm going to rewrite that. The denominator of the fraction is going to be the root, and the numerator is going to be the exponent. Now, it doesn't matter which way you write it. However, sometimes writing it in one way makes the math easier. So let's think about it. Do I want to square 27 and then take the cube root? Or do I want to take the cube root of 27 and then square it? I don't know about you, but to square 27 sounds like I'm going to need a calculator. It's going to be a really big number. So let's try to take the cube root first. So think to yourself, what times what times what is 27? And that happens to be 3, right? 3 times 3 is 9, times 3 is 27. So it's actually easier to cube root 27 first, and then we can square it. 3 squared is going to give you 9, and you're done.